going to have 2 talks. We have half an hour break. We have another 2 talks. We directly afterwards have our own discussion, 12 to 12:30. That is not recorded. Notice also we have from 2 to 3, we have 8 or 9 or 7 talks that are maximally 8 minutes long. So here it's Barbara, Eugene, and so on. So we have 7 talks actually of 8 minutes, 2 to 3. For those who participate in the reception tonight, at 4:15 the bell will ring. Please start marching because at 4:30 the bus leaves. Please check the email with the exact direction. It's up the hill where the bus is. What is that? That's the bell. Ah, the bell. So when you're up there on the whiteboard and you hear some bell, then you know it is time to start wrapping up.
And you should just lead everybody and just go, eins, zwei.
Yeah, but not everybody speaks German. So, okay, great. So we started our first talk. Welcome, Christoph.
Thank you.
Oh, that's very good.
So yeah, I'm going to talk about rings. Sorry, not semi-rings. Although, on my slides, I will point out sometimes, that this also works for semi-rings, and usually everything works for semi-rings, except for the ultimate purpose for which I'm developing this, right? So why do I want rings? So, I mean, this has come out of projects that I've been working on where we wanted to compile queries and where we really suffered from having so many different case distinctions when SQL was really a very messy language to us. And I tried to clean this up. Generally speaking, of course, nowadays with data science, people have come up with lots and lots of calculi and so on for numeric computations. I'm going to talk about my thing, which is in this case quite old already. Relational calculus and algebra are terrible for numeric computations, right? It starts with that, union is not even an operation, right? Certainly not a total operation because there's certainly pairs of relations that you're not allowed to union together, right? So we don't have a semi-ring. We certainly don't have an algebra. Cylindrical algebra, yes, but not an algebra. Aggregation is an afterthought, certainly in these core languages that we've been studying most, right? And one very experienced senior colleague of mine once told me about undergrads, that no matter what we do, they will never understand universal aggregation, universal quantification, right? So it's hopeless. And in my experience, having graded millions of database exams, I think this is true, right? And people, when you give them some universal property, usually, if they manage at all to realize that there is something to be done here, that is not just existential, right? They will do something like doing a counting query, right? I've dumbed this down, of course, this would be usually qualified in some way, right? But rather than saying, is it true that all, people understand for all, right? You ask, you count the guys who understand for all, and you count the people, and you compare that, right? And that's what people do, right? In a sense, right? And of course, I'm saying this as somebody who has, got a job basically based on working with logic, and maybe I feel like a traitor to you, but quantification is actually not that important to most people who use these languages, but aggregation is, okay? And there's things I would like to do, and for which I need rings as well. Particularly, I would like to be able to, express finite differencing elegantly, right? I would call this differentiation sometimes because it's easier to say, right? And this is key to many things. We did a lot of incremental view maintenance work, but you need this in other contexts as well. I mean, one thing that we have heard a lot about is semi-evaluation with data log. Of course, that's incremental computation, but there's all kinds of different versions of things like online and streaming, etc., that need this. And even just for, expressing, many, core query operator algorithms, that kind of applying a delta, is an important thing, right? And right now, if you try to figure out how to do this for SQL without any kind of cleanup, this is a very messy task. And that's why, when I started working on this, I don't think that people have been working on very large fragments of SQL to do things like incremental view maintenance. So here's a key tool, monoid semi-rings or rings, right? So let's assume we've got a semi-ring or ring A and a monoid G, okay? And I'm defining, finite support functions. That means functions, right, where only finitely many elements map to something else than 0, right? The 0 of the semi-ring A, okay? And I define the operations in this way. So I've got these functions, x, maps to alpha of x, is one of them, alpha. And the sum of two such things is just, the pairwise sum here, right? And the important thing, the multiplication is the convolution product, okay? And this is where the monoid plays off, right? We are basically saying, for an x, right, its value is going to be, for the product, split up in all ways that they multiply up to x, right? Gets y's and z's of g, right? And, sum up the products of these, alpha of y and beta of z, okay? And it's very straightforward to define a zero and a one, such we've got a semi-ring and a ring if A is a ring, okay? We call this a monoid semi-ring or ring, right? And if it's cumulative, it's also an algebra, so it's a monoid algebra. One thing that's worth observing, although it's very obvious, if you just take the plus operation of this of such a monoid ring, and you add some obvious scalar product, so you can multiply in, so to say, the elements of the ring, right? Then you've got a free module on G, okay? And with this, it's actually very easy to prove the following thing, right? So think of characteristic functions for every element of the monoid, right? I've got a function that basically, maps to value 1 for G and to 0 for everything else, right? And we say that some operation, we're going to talk about operations for multiplication here, over, in this case, the ring of integers, right, is conservative over the multiplication inside the monoid, right? If on these characteristic functions, it's actually just this product, okay? And in my opinion, that's what you always want, otherwise it would be very weird, okay? And if you make this assumption, there is actually just one way to build a product to get a ring, given the addition operation on such functions, okay? And that's this convolution product.
So, Christoph, it might be just me, but I don't understand this last condition, the conservativity. Can you explain again?
Right. So I've got the items of elements of the monoid, right? Remember my monoid ring, the elements are functions, right? Yeah. And there's special elements that look like these characteristic functions, right? Okay. And now I'm talking about possible multiplication operations for my monoid ring, right? I already showed you one, but I want to kind of justify it, right? So let's not constrain it yet, right? Let's say what multiplication function could I build? And let's just assume that I want to look at those that satisfy this property, right? That the product in my monoid ring of the characteristic functions of G and H is the characteristic function of G times H in the monoid. Okay. Yeah. We will later actually use tuples for these elements of this monoid, right? And then this is very obvious that that's what you want. It would be very weird otherwise, okay? And with this, and the fact that you've got these modules, you can very easily prove that there is just one way, namely this convolution product, to build a ring. Okay? Yes?
Sorry, I missed something on the previous slide. Could you go back? The multiplicative unit here. I'm confused. So why does it have finite support?
Well, it is non-zero only on the one element of G, right? So it has finite support. There's only one non-zero element. So yeah, okay.
Sorry, yeah.
I don't know. Is the notation bad? Right. Okay, good. So this is also all very basic, algebra stuff for the moment, right? And now let's apply this to databases, right? So we're going to build a monoid ring of relations, right? So what I'm going to, and remember, one thing I want to achieve is that union is a total operation. You might say, not a big deal, why do I make such a fuss of it? Because there would otherwise be gazillions of case distinctions when we do incremental view indents, for example, where we've got deltas, where union is something that is applied in many different and weird ways, including, doing differences, right? So record conceptually is a tuple with a scheme of its own, right? So a relation, in my context, could have records, tuples of different schemas, right? It's a set of tuples, and each tuple has its own schema, right? So it's a kind of partial function mapping column names to data values, right? And we call this T is the set of all records that I can build, right? Given a vocabulary of column names and a domain of data values, right? So we call it generalized multiset relation, a finite support function from tuples to elements of our semi-ring or ring, okay? And here's an example, right? So you see, there's two tuples that have, weight value or whatever, R1, R2, right? And this one is actually kind of a unary tuple, and this is a binary tuple, right? And I just bunch them together. And because they have their own schema, so to say, there's no problem with doing that. Yeah, it's just kind of polymorphic, so to say, these relations. And here is my monad ring of relations again. And I'm sorry, I'm basically very redundant here because I'm showing you the same stuff again here. Just I filled in now this concrete, structure here, right? So the monoid is now these tuples, right? And the operation, the multiplication operation of the monoid is putting them into singleton relations and joining them with natural join. Okay? And you again have the convolution product, etc., right? Everything else, the one element we have got these nullary tuples, these empty tuples, so to say the smallest possible tuples, right? And of course, joining them in doesn't change the thing. It's idempotent, so to say, right? You join this in. Yes?
So if you're just joining two individual tuples, not sets of tuples, what happens if they don't join, if they disagree on the common attributes? What is the result of the join?
Well, we're not computing this. This is not how the join works. The only way we are actually kind of using this monad operation is here. And if it doesn't match, we're not going to use these y's and z's, right? Yeah.
Are you using a commutative join?
This join is commutative, right? This multiplication operation is commutative, right? And of course, because we have a ring here, we also have a minus operation to the plus, right? So example, and I'm just showing you this again for reference, right? Suppose I've got these three generalized multiset relations, right? Let's take S and T and add them together, right? Well, I can, these two go together. So I get, for C, I get S plus T1. And for BC, I get T2, right? And now the multiplication, right? The thing is now, I have to look for every tuple here, right? That I want to construct. And conceptually, this is a very indirect thing. I have to think all possible tuples, right? But there will be only, finitely many that have non-zero weight, given that the input is so, right? I have to see all ways of constructing these tuples, right? So the interesting case here is this thing A2BC, which I can construct in two ways by joining, so to say, or multiplying R with S plus T, right? Because this thing joins with this, no contradiction. It also joins with this. Of course, if this was B prime, a different value, it would not join, right? And for that reason, I get, this sum here, right?
Sorry.
Yeah.
Why did it join with the first row of S plus T?
It's in this case, it's like a rational product operation, right?
Okay.
They don't overlap in schema. It's like a natural join, so to say. Yeah, it's a natural join, right?
So how should we read the missing entry? So under B, there's only one B.
So you could talk about null values. I don't think of them as null values. It's probably not clean to think of null values, right? I think of them as that these are not tuples, but records. They have their own schema, okay? So it's polymorphic. Each of these things is an object, each of these records that knows its schema and its local domain, right? Okay, so this tuple says, I'm a unary tuple on C, and this tuple says, I'm a binary tuple on B and C, okay? And why am I doing this? Obviously, that I can union together anything, right? So I've got a total operation. I can build a ring without having weird exceptions and weird things to say about it, right? Yeah?
Christoph, sorry for nitpicking, but you do want to have a monoid structure on the set of tuples.
Yeah.
So what is a binary operation that has to be defined for any pairs of elements in the tuples?
Yeah, that's this. It's the natural join on singletons.
Yeah, but the natural join is not always defined. So I understand you can define the convolution, but I don't think you can define the basic monoid operation, or at least I don't understand how you define it.
Yeah. Yeah, I mean, I have in the full thing, there's some kind of version of a fail, and I've built a monad around it, but I wanted to leave this out here.
Good, thanks.
Okay, so sorry about that, because I really don't need it for anything else. Yeah, so, and there is a semantics definition data where you see these things, but I will go over this quickly because otherwise it's going to be very boring for everybody. Okay, so, but yes, very good point. Sorry about being, trying to brush this under the rug. Right, so, yeah, so this thing is a commutative ring with 1, of course, and I've shown you this thing already. It has this minus operation, and it's also, if you take it for the whole numbers, right, the integers as the ring, it's the smallest ring, right, such that all relations in set of back segments are elements, right? And plus and multiplication generalized union and natural join, right? So in particular, if you apply this stuff, to just normal relations, this is exactly union and this is exactly the natural join. Okay. So this is not arbitrary, but that's the natural thing to do, right? So this is something that is exactly union natural join on normal relations, multi-set relations, back semantics, but also set semantics if you like, But it also works for these things that I get by basically putting items together that are, have different schema, Okay? And it doesn't do more than that. It just does exactly this. What? I think I'm running out of time. Okay. Yeah. So, well, you can build polynomials. You can distinguish elements which are variables and which are constant relations, of course. And you can talk about deltas, right? Just using distributivity, right? This maybe looks hard to read, but just a multiplication, right? I mean, suppose I've got some generalized multiplication and it's delta times some other plus its delta minus the old version, right? I just apply distributivity and I get these things, right? Okay. And one thing that is worth mentioning here is that you can talk about the degree, right? So if you've got kind of two variables here, it has degree 2, and the delta always has degree 1 less unless it becomes 0, right? That's important for this differentiation here. You can basically differentiate these things as many times as you like, but every time the degree goes down by 1. Okay. Okay. So one thing that I need next is a generalization of these things. These are again rings, but they are not going to be commutative anymore, right? They allow me to do sideways binding passing. Okay. And that allows me to basically have conditions which are by themselves not finite support. Okay. So that would be kind of infinite tables that I can join in, so to say, right? So basically what I'm going to have is, before that I had these things that are functions from tuples to ring elements. Now I've got functions from tuples to tuples ring elements. I think this is just a current form, but I think this first thing is going to be the bound variables, the input variables, and these are those that I can compute, the output variables, right? And given this is again finite support, right? And ultimately, you can prove in some way or other, essentially, that there's, again, only one way to build this, right? And what it basically does is, that's the interesting part, looks kind of ugly, right? That you can basically pass the output variables of one relation as input variables of the other, right? And otherwise, it's, again, this convolution product. This is, again, a ring, The associativity proof is kind of cute, also very, very easy, right? And this is something you can now use to kind of do things like, sideways binding passing, like in relational calculus. We can talk about safe queries, etc. Okay.
Sorry, Christoph. Why couldn't we get a inverse here?
No, we can't get an inverse.
Okay, you're in a semi-ring for some reason all of a sudden.
No, I want it to be as general as possible. I always talk about semi-ring, but it also works for rings, because they are also semi-rings. Sorry, if I didn't go do this consistently. No, I know. This is, yeah. No, this is, yeah, okay. In the title, I should have put the semi again in parentheses. Sorry. Yeah. Yeah, so I can do that. And since I'm running out of time, I want to speed up a bit. We have defined a language, right? And the important thing about this language is that it basically does all the interesting stuff of SQL. There is, of course, ugly stuff, that maybe, null values, we don't look particularly in outer joins and stuff like that, right? But it can do all the aggregations, and it can do universal quantification in particular, right? So we have these operations of the ring that we already have seen, right? We've got some ring elements, relations, atomic relations, but also functions like arithmetic functions and so on. And we can take variables, that we have basically, fetched, just like in relational calculus, and basically maybe if they are numerical, kind of make them part of something that we sum up. We've got conditions, okay? And there's semantics, and it's horrible, and I'm just going to show you that so this is the stuff that we have already seen before. Summation, right, is kind of a generalization of addition, of course, right? And the important thing is that they're basically saying, if I've got some variable, right, some tuple here, right, this sum is basically over y's that I can multiply in such I get y again, right? And as a consequence, what this means is that this is not just like a projection that counts the copies, right? it doesn't just compute tuples of maybe, where some variables have been removed, but also these where the variables are still in there, right? And if you don't want them, you just don't, query them further later on. And actually, this is the only way to do this so that you get a ring, right? Some of this stuff, it's impossible to read right now, right? But it was actually quite tricky. And in many cases, again, you can argue that this is the only way to do this, okay? So we have conditions, right? We also have something called lifting, where you can basically take, some query, right? And take the kind of stuff that is basically this multiplicity, right? The ring stuff, and lift it again and put it into as a data value into a column, right? Here's an example, right? And since I don't have the time, I'm not going to go for this, right? We can do deltas for all of them again. The ugly thing is the delta for the condition, because that basically just says in general, right? Add the new version of everything and subtract the old version, right? It's not a good, nice, efficient delta. On the other hand, if this alpha doesn't contain a subquery, right? No relational atoms, right? Then the delta is 0, okay? So in many cases, if you don't have nested queries or complex structure, this is actually easy, okay? And we can define degrees again by every, the degree of the delta is always 1 less or 0, right, than the degree of the input query, okay? So with that, we've done something that I want to quickly talk about, which is this what we call recursive incremental view maintenance, right? So if you've got this kind of difference operation, right, and we're talking about in this case, I've simplified this and basically look like an integer, right? We're talking about the successor element. In the case of relations, this is, the relation and the relation plus one tuple of your choice, right? So I want to simplify to kind of illustrate the idea here, right? What you can do is the following, right? Suppose you've got some polynomial, that's a query, right? You can talk its differences. You can compute those according to the rules that we have, okay? At some point, the third difference here is 0, right? What you can do is, as you go and, add to x some values, right? You can compute this thing, right? But you can always, compute this new thing as the old version plus the delta, obviously, right? And you can do this for the entire table, right? You can memorize the whole thing, right? So this thing is this thing and that thing, or this thing is this thing and that thing, right? And the thing is, we can compute incrementally values for this function without any multiplications. There's just additions and memorization, right? And the thing is, this, of course, a bit more notation you can do for our query language as well. That means you get rid of the joins. There are no joins in this thing. But you memorize multiple levels, of deltas, right? If you can afford this, you get rid of the joins. Okay. I have some example. In this case, I write it like SQL because there is a direct mapping to our language, right? And you can basically take such a query, and this is a very fast animation because I know I'm going to run out of time. I'm basically doing what we do here, on this example of SQL, right? I want to compute a delta for this query Q, right? So this is a TPCH-like schema, right? So I've got orders and line items, right? And I'm asking for the sum of the prices times exchange rate, so converted to one currency, right? Of the orders joined with line items, right? This in this case just one value, it's a zero-dimensional query, so to say. There's no group by in this case, but this also works for group by's. Okay, and the degree is 2 because I've got 2 relational variables here that I'm joining together. So I want to compute the delta as I, for now, insert a single tuple. In our work, we've built a system. We can also do batch updating and so on. It's more complicated. I'm not covering it here. But in this case, we talk about inserting. We can also talk about deleting single tuples now. In this case, for inserting an order tuple, right? So so I can express, and I've just written all of this in this language here, or in SQL. My delta, and I can start optimizing this, right? So this is the query, but I'm going to insert now a singleton, that's the delta, into this O, and now I'm going to simplify. This is just a compilation step where I simplify things, right? So I can pull this out. This is just associativity, right? And at some point, I'm done, and I've got a query that is, in this case, just degree 1, not degree 2 anymore, and I'm going to materialize this, and it's a group by query now for X order key, right? And I'm materializing this, and we have to incrementally maintain that one as well, right? So I give this a name, and I'm going to take this query again, and I incrementally maintain it, of course, for line item, because orders don't exist here. I can simplify and I get for all this some insert triggers. I can do this for delete triggers as well, okay? And in this case, you know, there are no joins. Well, these multiplications are on scalars, right? So this is kind of constant time updates, right? For this thing, for this query, right? And so in general, we have some compilation techniques here where we basically build these triggers. You know, this looks a bit like C, this thing we call this NC0C, because we can prove that everything, you know, the data complexity, so after compilation, is in NC0, okay? And remember, NC0 are, you know, constant depth circuits, you know, of bounded fan-in, right? And they have been separated from AC0, which is the complexity class that we best, you know for relational algebra, right? So we actually have a complexity theoretic separation that actually, NC0 is known to be strictly smaller than AC0. This is not a complexity theoretic assumption. This is one of the cases where we actually have separated the classes, right? And the incremental computation is possible in NC0, where it takes us AC0, or if you've got, you know, aggregation, even something slightly bigger than that, TC0, you know, for the non-incremental version, right? So there's a kind of a complexity theorem here as well. And yeah, we've built a system around, it's called DB Toaster. It still exists. You can download it and use it and play with it. There's a lot more in that system. A lot of work went into the compilation, into like doing this thing on a large scale and efficiently, and you know, for a large query language. But yeah, that's what we've done here.
Christoph, I recommend that you ask for a show of hands for how many people have used DB Toaster, because I haven't. I'm pretty sure many people here have.
One. Oh, wow.
Many more have.
That's nice. Well, thank you. That's good. Probably all the users in the room. No, actually, this is not true, because we actually got a lot of requests and so on. Yeah, but unfortunately, it never went beyond just some GitHub project. It's a lot of code, though.
Question. Acyclic schemas only, in essence?
No.
No
restriction of that kind at all.
Okay, I don't understand how you would disambiguate a cyclic schema in this.
So you have to understand one thing, right? You know, this grants Tsioglu ear-eating algorithm for proving that something is acyclic, right? You take a hypergraph and you start eating ears away according to rules, those that are very loose at the boundaries, right? The thing is, in our technique, you know, when I do this compilation, and every time I basically replace, you know, a relation by this kind of by this singleton tuple thing, right? This is the stuff that I'm filling in, and then I'm starting to kind of simplify, right? You know, I'm basically removing a hyperedge. But this is not restricted to acyclic ones. You just remove hyperedges, you know, and the query gets smaller and smaller, right? There is nothing special that we exploit for acyclicity here. It doesn't care. Okay. Yes. I'm sorry. Do I decide? No, I'm done with my talk. I'm already answering questions. Is this okay?
Sure.
Or should I say it? Yeah.
Like one slide about open things that, because of 2010, like the next step. So any conclusion? Just.
So this is a question now. Yeah. Okay. Because there are other people who raised their hand. Okay. Yeah. So well, look. The thing is, you know, we spent a lot of time on this, right? Building this thing, and we built lots of prototypes, and we sometimes rewrote it, you know, using new languages and so on, right? You know, we published this at different times. You know, we were thinking about doing a startup. You know, there was a postdoc. I did this stuff initially with Yaniv. We wanted to do a startup, then didn't happen, and he went to academia, and now it's Google. And later there was Oliver, that many of you know and have worked with, and we were thinking about doing a startup, and it never happened because it's just the two of us, you know, and you know, at some point, you know, we all kind of burned out of this project, right? No, I think there's no great. I mean, you know, the kind of cleaned up version of some things that I talked about today is actually not published. It's just a technical report. Maybe one more thing to do is publish this, but I'm not sure if anybody still wants it because it's like 10 years old and people have already moved on. And, you know, I basically have to kind of say, oh, but this is worth publishing because it actually happened before all these other people have done something very similar, right?
But I mean, DB Toaster is a benchmark for, I mean, people compare whatever approach they take to incremental view
It's certainly a benchmark for the students that worked on it and now have academic careers and are only in the business of like just saying how bad this is and how much better their thing is that you do now, right?
The guys at VMware and with Frank McSherry and this, I didn't bring up DB Toaster, but it came up because they were comparing. I mean, Frank at least was comparing what the materialized.io, how well it did compared.
You know, I never had the energy to kind of really do the comparison myself, right? Of course, Frank McSherry's work is beautiful, and it is a lot more general, right? You can do this for pretty much anything, right? But you know, all the stuff that we can do, you know, since we do a lot of static stuff, right? We in principle can be better, more efficient. Right?
So.
But I would say, I don't think you can get a paper accepted in Sigma or VLDB on incremental anything without comparing to DB Toaster.
I think that's the way it should be. Although I'm not a reviewer, you know.
It's a system to beat.
Okay, good. But I think you want, I'm sorry, you had your raise your hand.
Yeah, this question might be too half baked, so maybe we'll take it offline. But I was trying to understand, when you're avoiding the joins by maintaining that memo table,
Yeah.
what's the space-time trade-off there? Like, can you bound how big that table gets and what the costs are of moving that data in and out to work on it?
No, it can be quite bad.
So there's this thing, the REAP algorithm from like expert systems, this net thing. It reminded me a little bit of this, but I don't know if you've looked at that or if it's related at all at the right intuition.
I'm honestly not sure, but if I can, yeah. I mean, maybe I forgot because this was like 13 years ago that the last. But yeah, I mean, so the thing is, usually, right? These auxiliary views, right, have you know, they have this lower degree, right? And usually this is also reflected in the kind of number of relations that join together, right? So we can usually assume it's of course a question of which columns you have to keep, you know, and not project away, that these things are smaller, right? But it's still costly in general. And there's tricks, and we even have done this in DB Toaster, some trade-offs where you basically decide not to materialize certain things and do it in several steps. This is something we have done, absolutely, right? You know, there is a lot of things I didn't say because it's, unless you want to build this, it doesn't matter to you. But we had spent a lot of time on it. For example, this lifting operation, right? That takes basically something that is a multiplicity, right? This in this kind of multiplicity domain and lifts and puts it back into the data values in the table and so on. To do this efficiently, right, was very complex. The optimization operations of techniques for that and so on, right? And particularly, there's sometimes a trade-off to make where we say actually we don't materialize this thing.
Yeah. So please keep your questions. We have here these discussions. And let's thank again Christoph.